In this module, we're going to look at the center of gravity, center of mass, or centroid of a body. We need to understand where the effective gravity would act for a body to decide something like shown in this image, whether or not a block is going to be stable or whether it might topple and be unstable. In another application, we might wonder under what conditions will a dam, which is supporting a significant amount of water pressure behind it, is going to be stable. Or if we have a water tower, whether if you have a little bit of earthquake shaking causing some side-to-side motion, whether or not that water tower is going to be stable. To design the structure for supporting a water tank, we will need to know the weight of the tank and water, as well as the locations where the resultant forces representing those distributed loads act. So we need to find that one location that could be representative of the whole to make our task easier. How can you determine these resultant weights and their lines of action? That's what this module is about. Another concern might be the stability of an SUV when it takes a sharp turn. One of the important factors in determining its stability is the SUV's center of mass. Would you want the center of mass to be higher or lower to make the SUV more stable? The higher it is, the more unstable it is. So you'd want it to be as low as possible to reduce the chances that it would tip over. How would you determine the location of an SUV's center of mass? In this chapter, we'll be looking at the how in that process. Another structure that we might be worried about the stability of would be a goalpost, such as shown in this image. And it's important to note that look at the curvature of the supporting post. Clearly, integration is going to be needed to determine the total weight of the goalpost and to determine the location of the centroid. Notice that in this case, the center of gravity, if you try and imagine where a single point representing the mass of this entire structure would be, it's not going to lie directly above the supporting post. So knowing its location is something that we'd need to know. How to determine that is something that we'll be addressing in this chapter. Consider a stack of books on an edge of a table, and we can do this to try and find the centroid of the stack if we simply slide the books to the point where they're about to topple off the edge of the table. When we reach that point where it's just at the edge of getting ready to topple, we'll have found the centroid of the stack with respect to the direction in which we slid it. Finding the center of gravity by this method would work for any object, but would be slow and obviously imprecise, but it would work importantly. Why I bring this up is because it's a great way for you to visualize what it is that we're trying to get. The concept of the center of gravity requires us to consider each individual component of a body. So we might look at a differential component which we'll represent by dW. That represents just a small fraction of the weight of the entire body. So a body is composed of an infinite number of particles, and so if the body is located within a gravitational field, then each of the particles will have a differential weight dW. The center of gravity is a point often shown with the capital symbol G, which locates the resultant weight of a system of particles or a solid body. So it might be a body composed of different components, but if we're going to consider them as one entire body, then we have to consider each of the components. From the definition of resultant force, the sum of the moments due to the individual particle weight about any point is the same as the moment due to the resultant weight located at G. Why is that a big deal? If we know the location of the center of gravity and can consider the full weight at that point, then we've got one force acting at a single point instead of having to consider the individual individual particles that comprise the whole body. Also note that the sum of the moments due to the individual particles' weights about the point G is equal to 0. The location of the center of gravity measured from the y-axis, so now we have a particular direction in which we're trying to determine the location along a particular axis. It's determined by equating the moment of that weight about the y-axis to the sum of the moments of the weights of the particles about the axis. So if you consider a differential weight located at a point x tilde, y tilde, and z tilde, then you can find the location of the centroid along x as x bar times the entire weight w will be equal to the integration of x tilde times the differential weight. And so we've got an integration task to perform to complete this. Similarly, we can do the same calculation for the y-axis and the z-axis to find the three-dimensional centroid of a body. Therefore, if the location of the center of gravity with respect to x, y, and z-axis become these equations shown here. And for each one of these, you're going to need to form two completely independent integration tasks. And for a straightforward or regularly shaped geometry, it might be easy, and for others, it might be more complex. And in fact, it might not be mathematically possible to determine directly, and you may need to use numerical approximations. We're going to stick to more straightforward areas and objects in this module. So if we're trying to find the center of mass and the centroid of a body, we're going to be using these equations. But by replacing w with an m in the equations, then the coordinates of the center of mass can be found. So if we're not looking at a differential weight, but instead are looking at a differential mass, now you can get to the center of mass. Similarly, the coordinates of the centroid of a volume, area, or length can be determined by replacing w with either volume, area, or length. We'll mostly be looking at differential areas in this section, in this chapter, because we'll be trying to consider two-dimensional cross sections of a three-dimensional body. But sometimes we need to look at the entire volume, or in some applications, just look at conditions along a length. Let's take a look at the concept of a centroid. It's simple. The centroid C is a point defining the geometric center of an object. So that centroid C is shown for a rectangular, a triangle, a cylinder, and a quarter and half circle in the images shown here. The centroid coincides with the center of mass or the center of gravity only if the material comprising the body is homogeneous. That is, it has a constant density throughout. Many objects don't, but a lot of them do. So this is a simple, often the act of finding the centroid is sufficient to get the centroid when we're talking about a body with a uniform mass or a uniform density. If an object has an axis of symmetry, it's important to understand that the centroid of the object acts on that axis. That's a huge deal. Many of the geometries that we consider do have symmetry, and you immediately know that the centroid acts along that axis of symmetry. In some cases, the centroid may not be located on the object. That might seem a little odd, but if you'll remember the goalpost example in the image we had earlier, that would be a case where the centroid might very well not lie anywhere along the goalposts themselves. It's just going to be a point in space where we could represent the full weight of the goalposts. The steps to determining the centroid of an area are: first, we need to choose an appropriate differential element, dA, at a general point, x and y. And it's often important to recognize that if y can easily be expressed in terms of x, such as y is equal to x squared plus 1, then we should use a vertical rectangular element. If the converse is true. That is, if it's easier to express x in terms of y, then we should use a horizontal rectangular element. Next, we need to express dA in terms of the differential elements dx or dy. Third, we need to determine the coordinates x tilde y tilde of the centroid of the rectangular differential element in terms of the general point x and y, and then express all the variables and integral limits of the formula using either the x or the y, depending on whether the differential element is in terms of dx or dy, respectively, and then we need to complete the integration. Note that similar steps are used for determining the center of gravity or the center of mass. These steps will become clearer by doing a few examples. Example, suppose we have an odd-shaped area where we can define the shaded in blue area, where we can define the relationship of the top as y is equal to x cubed. So given the area shown, if we want to find the centroid location, both x bar and y bar, we should follow the steps outlined on the previous slide. Our solution would be, first, since y is given in terms of x, we should choose dA as a vertical, our differential area as a vertical rectangular strip. So we have in red shown here one differential strip where, in order to calculate dA, we need to take simply x cubed times dx. So dA is simplified in our case to x cubed dx, and that's going to make the process easier. It involves only then a single integration on x. So we define dA as y times dx, or x cubed times dx. Probably the most important step here is to understand that to get that differential area, we're just taking the base times the heights. What's the base? It's dx. What's the height? It's y at any particular point of interest. So we've just multiplied those together, and that is what turns out in this example to be equal to x cubed times dx. At the end of our task, we can say that x tilde is equal to x for this point, and y tilde is equal to y over 2, so we're halfway up the object, and that's equal to x cubed over 2. To continue with this example, if we perform the integration tasks that were outlined at the start, we see that we need to integrate across an area. So this would typically be double integration, but because we've expressed x in terms of, because we've used a strip, it's going to be simplified to integration, a single integration. We're going to integrate on x. In the numerator, we have an integration from 0 to 1, because that was the extent of our body. And then we're going to have x times dA, which is simply x times x cubed dx. In the denominator, we don't have that x in front of our terms, so we just have to integrate from the same limits, x cubed times dx. So we have two different integration tasks to perform. There are different functions in the numerator and the denominator that we need to integrate. But when we complete those tasks, we then take the ratio, and we'll have found the centroid along the x-axis. Similarly, if we want to find it for y, we have to complete the integration tasks using y tilde in the numerator instead of x tilde in the numerator. So we end up with the centroid by completing these two integrations and then taking the ratio. So we found the centroid of a relatively simple but sufficiently complex to require integration object. If the integration involved in the previous example created a bit of a concern for you, then I can help you relax, because what we're going to emphasize in this module is composite areas, and we're not going to need to integrate mathematically. We have a simpler approach. Composite bodies are, for example, beams with cross sections such as shown in these cases. The I-beam on top or the T-beam shown on the bottom are commonly used in various types of structures. And when we're completing a stress or deflection analysis for the beam, we need to know the location of its centroid. How can we easily determine the location of the centroids for different beam shapes? By considering the fact that they're really, in both of these cases, these beams are really comprised of a collection of rectangles that are put together. Rectangles are actually easy to find the individual centroid of. It's in the middle of the cross section of a rectangle is where the centroid is. But when we put some of them together, we need, and we do this a lot, we need to be able to figure out where the centroid of the composite beam is, or when we put the several different rectangles together. Another example would be looking at a compressor, which is composed of various individual components, each with its own weight. In order to design the ground support structures, the reactions at blocks A and B have to be found. To do this easily, it's important to determine the location of the compressor's center of gravity. If we know the weight and the center of gravity of individual components, we need a simple way to determine the location of the center of gravity of the entire assembled unit. Now let's look at how to find the center of gravity or the center of mass of a composite body. Consider a composite body which consists of a series of particles or bodies as shown in this figure. The net or resultant weight is given by the weight of the resultant is equal to the sum of the individual weights. We've seen that before. By summing the moments about the y-axis, we get x bar, the distance from the y-axis, times the individual weight of the resultant body, can be comprised of the x tilde, the distance to the individual particle 1, times the weight of 1, plus x tilde 2, that distance to individual particle 2, times the weight of 2, and then sum up the individual components, where x tilde 1 represents the x-coordinate of the weight of the mass of the first object, etc. Similarly, we can sum moments about the x and z-axis to find the coordinates of the center of gravity using these expressions. So here we're taking each of the individual particles or parts of a body and summing the individual components separately, as shown here. When we were doing this with differential areas in the previous example, it might have seemed a little complicated. But if you were dealing with your particles dealing with something more straightforward like a circle, a sphere, a rectangle, or a triangle, then calculating the weights and the distance to the centroid of an individual component aren't as complex. If we replace W with M in these equations, then the coordinates of the center of mass can be found. And that really isn't any different usually. Look more at the concept of a composite body. Consider these two objects. Many industrial objects can be considered as a composite body made up of a series of connected, simple shaped parts, like a triangle, a rectangle, or a semicircle, or holes. Knowing the location of the centroid or center of gravity, CG, of the simple shaped parts, we can easily determine the location of the centroid of the center of gravity for more complex composite bodies. And now I'll outline those steps. This can be done by considering each part as a particle and following the same procedures outlined in section 9.1. This is a simple, effective, and practical method of determining the location of the centroid or center of gravity of an object, part, or machine. First, divide the body into pieces that are known shapes. If you have a hole, you consider that as a piece of the material with a negative weight. So first you'll add the whole object that has the hole, and then you'll remove the portion that is the hole. So you'll have a positive weight followed by a negative weight in that hole, and that will take care of considering a hole in an object. We make a table for the first column, with the first column for the segment number, the second column for the weight, mass, or size, depending on the problem, and then the next column for the moment arms, and finally several columns for recording the results of simple intermediate calculations. Then we'll fix the coordinate axes, determine the coordinates of the center of gravity of a centroid of each piece, and then fill in the table. Then finally, we'll sum the columns to get x bar, y bar, and z bar, and we'll use formulas such as x bar is equal to the sum of all the x tildes times the area divided by the sum of the areas, or if we weren't dealing with areas but weights, then we would find the center of gravity using the appropriate weight column instead of an area column. It'll become more straightforward after doing some examples. This example, where we have a three-dimensional body that's composed of a triangle, a triangular slab, a rectangular slab, and another triangular slab. So we'll follow our same steps that we just outlined for analysis. In this problem, the three blocks can be understood as three pieces shown here. A and C are both triangular slabs, and B is a rectangular slab. The volumes for each shape could be found using simple conventional formulas. For A, we find that it's half a meter thick. We see that one leg has a length of 1.5 meters and the other leg has a length of 1.8 meters, and because it's a triangle we have to multiply by a half, giving us a total volume equal to 0.675 cubic meters. For volume B, it's a rectangle, so we just need to get one side, the length of one side, which is 2.5 times its height, which is 1.8 meters, times its thickness, which is 0.5 meters, to get its total volume of 2.25 cubic meters. For the volume of the triangular slab C, we take its thickness, 0.5, times its length, 1.5 meters, times its height, 1.8 meters, times the 1/2, because it is a triangular slab, because there is a triangle involved. And for that slab C, we again get a volume of 0.675 cubic meters. If we then complete the table that the instructions asked us to, we can find for each of these segments, A, B, and C, we can now write their volume. We then need to locate the individual centroids of each individual slab, and you can see, you would know where the centroid is for A and C using the 1/3 away from the longer base. And you can use that formula to find the centroid of each of those slabs, and we know the centroid of the rectangular slab is right in the middle of that slab, so we can find these distances from the y-axis, the x-axis, or the z-axis as shown. We would then be able to multiply the x tilde times the volume, or the y tilde times the volume, or the z tilde times the volume, and extend to those columns. Finally, we can sum up the individual columns, and we're just one step away from finding the x bar, y bar, and z bar by taking the ratio of the three columns shown on the right divided by the volume 3.6 cubic meters, and you'll have x bar, y bar, and z bar. So to complete this example, we take the bold portions of the table that we had on the previous slide, and we're now able to calculate x bar, y bar, and z bar as the ratio of the different columns. So 1.406 over 3.6 gives us x bar, etc. So now we know the location of the centroid of the composite body, which is made up of these three individual segments. In another example, let's take a look at an object that actually has a hole in it, so you see how to handle that type of case. We'll use the same tasks that we had before, but our composite bodies are now going to consist of 4 parts. First, we'll have a triangle shown with the symbol A. Then we'll have a rectangle shown with the symbol B. Then we'll have a quarter circle C, followed by a negative semicircular area D. So now you're going to see how to incorporate a hole. Next, we're going to take the step of creating the same table that we used previously, but we'll now consider parts A, B, C, and D. And remember that D is a negative area. So here's our table that results from our calculation of the area, x tilde, which is the distance from the y-axis, or y tilde, which is the distance from the x-axis, and then we have the moments x tilde a and y tilde a. And one thing I'd like to point out is you would know the formulas, perhaps except for where to find the centroid of the quarter circle and the semicircle. You could use a table to get those, but in the composite bodies that I'm actually going to ask you to consider, you'll only need to consider triangles and rectangles, and I think it would be fair to add in a full circle, because you'd know exactly where the centroid is and you'd know how to calculate the area of a circle. By the way, the centroid of a full circle is in its center, at its center. So take a look at the formula, make sure you know how to calculate each one of these components. Let me pick one example. Of each type. Let me pick y tilde for triangular slab A. We'd need to find the centroid up from the x-axis, and we know that when you're looking at the centroid of the triangle, it's 1/3 of the way from the longer side to the shorter side, so it would be 1 inch up from the x-axis. So that's why we have y tilde of 1. For the rectangle B, notice that, let's do both x bar and x tilde and y tilde. Where B is not just a rectangle, it's actually a square that's 3 inches by 3 inches. So if we want to find out what x tilde is, we'll find that it's 1.5 inches to the left of the y-axis, so x tilde is minus 1.5, and it's 1.5 inches above the x-axis, so y tilde is also 1.5, but this time positive. Similarly, we have expressions for the quarter circle, but I don't think you'd know these off the top of your head, but with the table you could find these. And last row, or the last particle that we need to consider, is the semicircle D, which notice I describe as a negative area pi over 2 because it's a hole taken out of the other parts. Whereas it's the centroid of D, the x tilde, I would like you to be able to recognize, lies along the axis of it. The y-axis is actually a line of symmetry for the semicircle, so that's why we have x tilde being equal to 0. I would not expect you to know how to calculate the centroid of a semicircle or a quarter circle, but with the formula you would be able to find those. I'm sure you'd recognize. Once we complete these tasks, we have to sum up the individual components. The only thing that's different really here in this example is notice that the semicircle has a negative area, and you just add when you should add and you subtract when you should subtract because of the sign of the number. So you just sum up the individual columns that we have in the 3 bold blue numbers that we need in order to find the centroid of this composite area. So now we can use the table result in order to find the coordinates of the centroid. Those 3 bold blue numbers from the previous table are shown here. We can find the x bar by using x tilde times A divided by the area A, or minus 22.5 divided by 19, to find the location of the centroid, which is shown with the red capital C in the image shown here. Similarly, y bar is the sum of the y tilde a's divided by the sum of the areas. So notice that the denominator is the same for both of these terms. We just use different columns in the numerator. And that's how you handle a composite area. These we do want you to be able to calculate.